Hello everyone, welcome back. In our previous video, if you remember, we discussed the linear regression method and we saw how it forms the foundation of predictive modeling in machine learning. But what happens when the data is not linear? And linear, I mean when the relationship between the input and output is not linear, or when you have more features than the number of observations. So today we are taking that knowledge to the next level, and I will introduce a very interesting trick in machine learning which is called the kernel trick. So think of this as a natural evolution of our linear regression journey. While linear regression works in many cases, the real world data often demands more flexibility. The kernel trick gives us that flexibility by building on the same mathematical principles we discussed last time, but with a fascinating twist that let us work in higher dimensions without thinking too much about the computational burden. Let's begin by reviewing the data structures, and then we will see how we can transform our previous linear regression approach into something even more powerful. So we have n training points in d-dimensional space. Here n represents our sample size, the number of observations in our dataset, while d represents the dimensionality of each observation, the number of features or variables we are working with. Our data matrix X has dimensions n cross d, where each row represents one observation. This is a crucial detail because it affects all our subsequent matrix operations. The X transpose has dimensions d cross n. We can form two types of matrices. X transpose X, which has a dimensions d cross d. This represents the correlation between features. Remember, d represents the number of features you have. The second matrix we can form is X transpose. This one is an n cross n dimensional matrix. This represents the similarity between observations. Remember, n represents the number of observations. Let's examine why these matrices are powerful. X transpose X captures the covariance structure of our features. Each entry, ij, tells us how correlated features I and j are across all observations. This matrix has dimensions d cross d, as I described before, which means when we have many features, for example large D, it becomes computationally expensive to work with. X transpose, on the other hand, captures the similarity between observations. Each entry ij represents how similar observations I and j are across all features. This matrix has dimensions n cross n, as I previously described, and becomes our focus when we move to the dual formulation. If you remember, in linear regression, we work with this simple equation, which is y is equal to x beta plus epsilon. Y is an n cross 1 dimensional vector of outputs. X is our n cross d dimensional data matrix. Beta is a d cross 1 dimensional vector of parameters, and epsilon is a n cross 1 dimensional vector of errors. If you remember how we find the best solution for the beta estimates is using something called the least square method. The ordinary least squared solution minimizes the error. So if you remember our previous video, we discussed how can we solve this equation to guess the best estimates for beta. We take the derivative with respect to beta and setting it to 0. And finally, we get the formula for beta. Notice that we need to invert X transpose X, which is a d cross d dimensional matrix. So when you have more features than observations, or in other words, when d is large, this becomes computationally expensive. And the complexity for computing this matrix is ODQ. So in modern applications, we encountered this problem when we have more number of features, when you have features which are more than the number of observations. or mathematically when d is very, very large than n. And this creates several problems. Number one, x transpose x becomes singular, non-invertible, when d is greater than n. Number two, even when invertible, the solutions is often unstable. And three, computational complexity scales with d cubed, becoming prohibitive for large d. So what do we do? This motivates us to use something called the regularization, where we can remove the uninterested features or reduce the complexity of the model and eventually use something called the kernel tree. So one of the ways for regularization is called the ridge regression. Ridge regression addresses these issues by adding an L2 regularization term. And so the objective function becomes this. If you solve this formula, you get the expression for beta, which now depends on this regularization term lambda. The regularization term lambda ensures invertibility, even when d is greater than n, as all eigenvalues are now shifted by lambda. Okay, now comes a crucial observation. Instead of working with x transpose x, which is a d cross d dimensional vector and depends on the number of features, we can work with x transpose, which is a n cross n dimensional matrix. This is particularly advantageous when n is less than d.
So don't worry if that feels a bit abstract. The real intuition unfolds next. After some algebra, we derive an expression for alpha that involves our regularization parameter lambda. Here we introduce the kernel matrix K, which is defined as this. This n cross n matrix is built from inner products. Each entry measures the similarity between observations I and j. These similarities are key. K is symmetric, positive, semi-definite, and every element reflects how alike two data points are. But here's where things get really interesting. What if our data exhibit non-linear patterns? Imagine our original data lives in 2 dimensions, yet the relationship between features is non-linear. To capture this, we can explicitly map our data into a higher dimensional space using a function phi. For instance, with a polynomial kernel of degree 2, our 2D data might be transformed into a 6D feature space. The beauty of the kernel trick is that even though the feature space can be huge or even infinite, the kernel matrix K remains n cross n, since it only stores pairwise similarities computed by our chosen kernel function. Now here's where the representative theorem comes in. It tells us that even when working in an enormous or infinite dimensional space, the optimal function that minimizes our regularized risk can always be expressed as a finite combination of kernel functions centered at our training points. This means that whether we are using a simple dot product, keeping us in our original space, or a more complex kernel like RBF, our solution always takes this elegant unified form. When it comes to prediction, the process is equally neat, with our coefficients alpha computed as this formula. A new observation x star is predicted through this formula. Here, the same kernel K is used both in forming the kernel matrix and in making predictions, ensuring consistency across the model. To sum up, the kernel trick allows us to implicitly map our data into a higher dimensional feature space, where non-linear relationships can become linear, while working only with an n cross n kernel matrix. This representative theorem guarantees that the optimal solution is always expressible as a sum of kernel functions. This framework not only simplifies our computations, but also provides a powerful unified approach to handling both linear and non-linear models.
So we have explored how the dimensions of the data and matrix operation naturally leads to the kernel trick. So this video was mostly about the motivation for the kernel trick and understanding the dimensions and the matrix operations. And in the next video, we will discuss the particular examples of the kernel functions that we can use, and we will see some practical examples and some code used to see how we can solve some complicated functions, the fitting functions, using the kernel method. So I hope that you learned something interesting from this video. The video was a little bit more mathematical. My goal is to have a good understanding not only about the intuition but also about the mathematical foundations of these models. Please like this video and subscribe to my channel for more content like this. I will see you in the next video, and until then, take care.